Thanks for joining me for this session titled The Expanded Guide to Plastic Part Design. My name is Ed Honda. I am a product development contractor based in Chicago, Illinois. I have 42 years of plastics and product development experience, and I can appreciate that there are many levels of expertise sitting here in the room, and I hope that all of you will walk out with something new that you didn't walk in with before. So let's get started here. What we'll be covering today, I'll be demonstrating the SolidWorks Fastening Features toolbar, review some basic design features using an electronic enclosure as my example. I will discuss part design improvements and added value to the electronic enclosure design with some slight cost increases in the tooling. I think you could get a lot more value added. I'll show you how to use the SolidWorks mold tools, whether you use it as a tool designer or I like using it as a design verification tool in the parts that I design as well. And then I'll just review using SolidWorks simulation. That's also SolidWorks Plastics. SolidWorks was the predecessor to the new plastics add-in that is available in SolidWorks now. And so I'll show you a bit of what you can get out of that as well. Okay, using the Fastening Features toolbar, there are some common features that you will create in SolidWorks that these tools make it a lot easier for you to create these features. Also, there is the added function of these different tools that you can save favorite configurations of bosses, reveals, snap fits, so that you could use them over and over again without having to recreate them each time. The Fastening Features tools, one of them is the snap hook and groove. I'm sure you've seen a lot of snap fits in various types of consumer commodity packaging, and I will try to give you an idea on how to use some of these different tools. So I'll start off with the snap hook and groove tools. I have a basic plastic enclosure here. I'll just roll back in my feature manager tree and recreate these different features here for you. Okay, so I'm going to be starting by applying the snap hook to the lower half of this enclosure. Use my snap hook tool. I mentioned that I can save favorites. I have a library in my C drive that I use to store all my favorite features. So I just selected that. Now I will go in and start with the basic location of my feature. Next, I want to place my snap hook at a certain angle. I have a couple features, reference features that I had put in previously that I'll just use to get this started quickly. Now I want to orient the snap hook a certain way, so I'll use the right plane as my reference feature to get my snap hook pointed in the right orientation. Once I have that, I'll just hit the green check mark, and what I have here is the snap hook. Now, one of the things I want to point out to you is I made this front surface of the snap hook parallel with the outer wall. there is a purpose for that, and I will show you that a couple steps downstream here. But now that we have the snap hook, I will add the cover again. Go back to my fastening feature toolbar, look for the snap hook groove, and what the snap hook manager is asking for is for the groove, what snap hook do I want to mate up with. So I'll just click on my snap hook. Second, I will select the body that I want my groove in, and you can see in the preview that I have the groove located on the inside of the cover. Hit the OK. And now I have the snap hook and the snap hook groove. Any questions? Okay, good. Okay, now to create a moldable feature like the snap hook and groove, you do have to add these openings here for shutoffs that will help you create these other features. So the snap hook and groove tools will only take you so far. It'll get your basic geometry of the snap hook and its groove, but you do have to go in and add a few additional features so that you can mold it in reality. So you do have to have some concept of various shutoffs and what to do in your tool steel, and we'll cover that a little bit further on as well. Okay, the lip and groove tool is an aesthetic feature, but it is also functional in that if you are assembling two halves of, say, a plastic box like this, it may not be a sure thing that you will get a good assembly of both your top and bottom lining up correctly along the seams. So what you do is you make a deliberate reveal to mask any sort of mismatch that you might have between the different parts. The differences can be created by your top half and bottom half being run at different times with slightly different process conditions, so your shrinkage could be slightly different. It's not necessarily, you're not necessarily going to be using parts that are made at the same time. You might have different types of stocking methods where one lot of parts could get mixed up with another with slight dimensional variation. So the reveal helps you to hide these mismatches. Okay, here's misalignment. Let me go back here and I will get this started. Okay, here I am at the point just before I add the reveal. I pick the lip and groove tool, load my favorites. I select the top, the bottom half, and then the mating corresponding surface between the two parts. And this is simply the face, the mating face between the two halves. Now for groove selection, I will select the surface that I want my groove to be, also the edge running around the perimeter of the cover. Now you can see I do have a preview in yellow, and that is showing me where my groove is going to be. Next, what I'll do is I'll go down and select for lip selection the plane that I want my lip to be located. And here again, I select the edge that I want my lip to go around. The preview looks good there as well. Click the green check mark. And now I have my lip and groove added to the two halves. So you can see that they mate together properly. The lip and groove is created in pairs. So what you can do is, like I have here, depending on my wall thicknesses, here at the bottom where it says favorite, I have different favorite lip and grooves for 100 thousandths wall, 78 thousandths, 60 thousandths walls. So I just have to bring those up, and I don't have to recreate those each time that I need the reveal. Any questions on this? Yes? You would create the features in the parts themselves. You would not add it at the assembly level. This is a multi-body part. Yeah, so a top half and a bottom half. Good question. Thank you. Okay, so here again, the reveal hides any misalignment between the two assembled parts. I'm sure you've seen this type of a seam in various types of consumer products, of all sorts of varieties here. Oh, if you want to have coincident edges running around your part, what is good is where you have your groove being created, add an extra layer the same thickness as what your cutout is going to be running along here. That way, once the groove and the lip are being created, you will have the same footprint running around the perimeter on both the upper half and the bottom half. If you do not add that, this area will be cut away by the lip groove tool, and it will not be the same perimeter top and bottom. So add a little extra material that gets trimmed away. That will give you your the same perimeter on the top and bottom halves. Excuse me? Just multi-body part. Yeah, I would do it as the multi-body part. That way you're self-checking yourself at each step. Okay, now bosses. Here again, I have a number of different favorites that I have stored away in my on my computer. This one I use quite a bit. Okay, and here again, I'll roll back. I will go and select my mounting boss tool. Go down, and you can see here that I have various boss geometries that I have stored away in my own design library. But I'll start here with the boss on the back side of this enclosure. Pick the location of where I want my boss. I had a 3D sketch here that I created prior to my boss location. Now you can see the fins on the boss are not aligned. So what I do here is highlight the box under fins and then find a reference feature. I'll use this tangent point along the back side of the rear half here. Click on that and you can see how the boss fins have reoriented themselves. Click the green check. My boss is created. Any questions on this? Excuse me. Yes, you can. Yeah, you can't select it in the boss manager tree. So you can also select the different heights, the thicknesses of your fin geometry. You do have to go in afterwards and add chamfers if you want them to be angled gussets. So that's a separate operation. You just use your chamfer tool. Now to come up with a, yes?
By selecting the vertex on that radius.
Right.
If you happen to change the radius, wouldn't you get an error?
Oh, I would think that, I would say that if you have a tangent point like that with a different size fillet, it would use that as a reference. But yeah, I would, it's not a sure thing. I would have to try playing with that. That's a good question. You can pick a reference sketch or some other feature that would give you the orientation that you need. I'm sorry, one more time, please. Okay, if I understood you correctly, like the diameter of the boss itself, it would depend on the functionality of the boss. If you're only going to be using like a self-tapping screw going into the boss, you can probably get away with a smaller ID. If you're going to be adding an ultrasonic insert into the boss here, typically you have a minimum boss diameter that the insert manufacturer recommends for hoop strength and mechanical bonding of the insert into the boss. So that will vary, but let me just backtrack here for a little clarification. See, here, my favorite for this particular boss, you can see where all my fields are filled with different dimensions. These I had to do ahead of time. And then I go down here and just save the favorite. This is for an 832 screw. You can see boss screw side 832. So that's something that I researched before I created the boss. And I looked up what type of a hole I needed for a clearance hole on an 832 screw. So that's where that hole comes in. I will show you something momentarily regarding that. But let me continue with this here. Okay, now I want to create a corresponding boss on the front half. Okay, so you can see that one thing I want to call out is that the front surface of the cover is curved, so that will have an impact on how I create the second boss here. But I'll go back to my fastening features, select mounting boss again, and then go to the favorite for the corresponding boss. Come back up here. I will select the surface that I want it on. Next, it gives you the option of lining it up with a corresponding boss. So I'm going to pick the edge of the first boss I created, and you can see that the boss shifted slightly, so now it's in proper alignment, axis to axis. Now, because of that curved front surface, the boss was created on an angle. The two adjacent faces on these two bosses are not properly aligned. So what I'll do is I will go back to the positioning text box here and select the front plane, flip that around, hit the green check mark, and you can see where it now is aligned. Let me fix a feature that I forgot here. On the fin orientation, I'll just use one of the other fins from the other boss. Okay, I knew it would blow up. Let me just clear this again. Okay, I misaligned I didn't align the fins on the second boss, but I would just use this feature. Sorry for that little oversight there. But are there any questions at this point? Okay, you were able to follow that. Excuse me? Yes. Yeah, this is, whenever I do mating plastic parts like this, I always start it as a multi-body part. That way, if you make any changes to one half, it'll be made on the other half. And then at a higher level, the assembly level, changes that I make at the part level will be reflected higher up. So that's how that works. Okay, a design tip. I would leave a gap between 10 and 20 thousandths of an inch between the faces of your bosses. Again, if you have slight shrinkage differences between different lots of parts, you do not want to have a sloppy fit where the two faces bottom out before the screw is completely seated. So this way you're always going to be in a bit of tension, but you'll always get a much better mating of your two halves. They'll always be tight. Okay, now what I'm doing here is I will use a basic electronic enclosure design, and it meets all your basic design intent. But it's very straightforward, very simplistic. You have a circuit board that is being mounted to the inside of the enclosure. I am using 4 self-tapping screws that are going into a boss. That's a pretty standard method of mounting a circuit board in an enclosure. I have vent slots on the backside to help dissipate heat that the circuit board is creating. I have a membrane switch in this recess with a back-printed overlay, decorative overlay. So it's a pretty standard electronic enclosure design. But what I want to show you here is with some additional minor costs to the tool, I can add a more advanced vent design where rather than just an open slot where moisture can be directly shot into the back of this enclosure, these actually protect and shield moisture from getting in. I worked several years for a company named Life Fitness. They manufacture high-end exercise equipment. And when in a health club, if you go around with spray cleaners cleaning off the equipment, we were ending up getting shorts on the circuit boards because of liquids coming in. So rather than a straight access slot, we went to a more protected design here. So that's an enhancement, and it doesn't really cost that much to burn that into the tool. Also, to align the two halves of the enclosure, I have these little posts protruding up at the reveal, so it helps to align and keep the two halves from shifting over themselves if there's any sort of loads applied to the front surface of the enclosure. I mentioned there's a membrane switch up in the front there, so when you're pushing on it, you could be flexing the front half, but it will help. These little posts will help keep everything seated, and that really does not cost you a lot of money in adding it to the tool. So here's a side-by-side comparison, straight slots versus the improved design where moisture would be harder to find access. Rather than using 4 mechanical self-tapping screws to mount the board, I'm using a snap fit over here on this part where I do not have to stock screws. I don't have the labor required to drive 4 screws. All I do is just snap the board in place. Little snap hooks are used on the edges of the board. So all you do is snap that down onto the mounting bosses with no hardware. Also, on this design here, I show where I have ribs going up to the top of the boss and the top edge of the part versus the boss just dead-ending at the end of the boss like it is here. One of the issues that you can have with a boss that's freestanding like this without any sort of interface with the outer edge, which is your parting line, you can trap air inside a dead-end mold feature that would create your boss. So what you want to try to do is these ribs over here allow any air that is trapped in the boss during the fill portion of your cycle. It lets you vent out through your parting line. So there's less chance of you having trapped air at the end of your boss. What can happen is if air is trapped in the boss, the air trapped will increase in pressure, it will heat up, and it will cause what's called dieseling. And you can burn or degrade the material at the end of your boss. So it's always good to have adequate venting for boss features. The other way of venting a boss with a cord hole like that is through the core pin itself and how it's mounted into the mold base. You can vent through that assembly feature between the core pin and your tool. But this really helps make sure that you do not get any air trapped in your in the dead end boss feature in the tool. Okay, now using SimpleWorks or SolidWorks Plastics simulation, this gives me my flow front vectoring on how the material fills the tool cavity. And here I have the basic enclosure where you can see from the gate the flow front is propagating itself out to the outsides of the part. Now, your part design here with the vents being in the horizontal, what can happen is in this enlarged view over here, you can see some of the flow vector arrows actually doubling back. It's coming out and then back towards the center of the part. This is called a backfill condition, and it's something that you would want to try to avoid. Okay, here at the vertical vent slots running along the bottom here, these flow vectors are more in line with the slots, so you don't get a backfill condition because the material here is coming up through between the slots, and then also you have a wave front coming back around. You want to try to avoid that because it will create severe knit lines in a vent area like this. So just your part geometry and your features can impact good flow of your part with the gate located in the center there. Any questions on that? Okay, good. Okay, and here again, Simpo and SolidWorks Plastics do allow you to see where your knit lines are going to be. And this is what the backfill condition has created. You have a pretty severe knit line between the slots that are running horizontal, whereas where they're running vertical, you have very negligible knit lines that would be a possible structural problem with the back half of this enclosure. Now here's that conventional method of mounting a circuit board. I'm using 4 self-tapping screws, thread cutting screws, and what I want to try to show you is there are other ways of doing the basic board mounting in your enclosure. I'm using molded in features to capture the circuit board inside the enclosure. I am not using any screws to mount that a circuit board. I do have a mechanical fastener here just as an option, but the board is captivated between a boss that is molded on the front half of the enclosure, and here is another boss that is mounted on the back, molded on the back half, and the board is just sandwiched between those 2 boss features. And here is a close-up of the snap features. I'm using a snap hook here, plus a boss with a slight extension that will go through the mounting hole in the circuit board. And once I press the circuit board down, the snap hooks will engage the top surface of the board, and I don't have to waste time, labor time, installing 4 screws. I do not have the material costs of the 4 screws, and you don't have to support the inventory in your for the screws. So it is a cost. You pay for these features up front in the tool, but you save money in the long run because you do not have to support using the screws in the mounting of the board. Any questions on that? Yes?
You've got something that's subject to moisture, you use lifters to create snaps rather than that bypass. You didn't want the holes in the back.
You can use lifters, but that's lifters are a more complex way of tooling something up where you do have undercuts. But that's another story. We can always talk about that more if you want to go into it further. Okay, but here I'm trying to show there are different ways of doing the same thing. You don't have to stay with the conventional mounting screws. You can use various types of molded in features to do the same function, and there are different types of cost and labor benefits by molding in these parts. Again, you'll have to pay a bit to get those put into your tool up front, but in the long run you will save labor and the hardware costs. Now 3D Content Central is something that I use quite a bit. Also, there are a lot of companies that have supporting hardware. I use 3D Content Central to find mold bases when I do have to design a mold. So there are a number of companies like DME, PCS that do contribute 3D models to 3D Content Central, and it makes your job a lot easier. Here's an example of an ultrasonic insert supplier that I use quite a bit. It's Emhart Dodge, but there are other companies with comparable products to the Emhart. But this is part of their website for the ultrasonic inserts. And you can see here that you can actually download SolidWorks parts, SolidWorks models of their ultrasonic inserts. You can ask for the specific size of insert and download models that you could incorporate right into your CAD models. The information that you get from the website will also give you the data, the information that you need on the hole geometry for your pilot hole. It's always good to follow this and incorporate this into your 3D CAD model where you're going to have your inserts located. Once you start downloading your inserts, what I have done here is I've created a folder in my design library where I have 4 different series of ultrasonic inserts. They all have slightly different geometries with slightly different features. But what I have here is I download all the parts and I create folders of the commonly used insert sizes that I regularly incorporate into design. Typically I use from 440 to quarter 20s in most of my part designs. So I have all those inserts loaded in folders right embedded into my design library. And here one suggested approach on modeling your parts where you are using ultrasonic inserts. You should incorporate the pilot hole that your spec sheet, the data sheet on each individual insert recommends for the pilot hole. You can create a configuration in your model, call it as molded here. From here, what I do have is I have a second configuration with my insert installed in my plastic part like it is here, and then this reflects how I want the part to come in, the enclosure to come in with the inserts from the molder. The molder typically has a lot of equipment for secondary operations like installing the ultrasonic inserts. So just the way our bills of material were like at Life Fitness, we would want the inserts installed at the molder. So this is how I would configure this part to show how I want the parts to come in from the supplier. Any questions on that? Okay, good crowd. Okay, now the mold tools and part design validation. I mentioned previously that I do design tools, but where I use the mold toolbar, but I also use the mold tools as a design validation of the part itself. So if I can get a clean core cavity split through all the different details and features in the part, then I know I've done my homework and have designed the plastic part correctly. Mold shutoffs to produce protected vent slots. You can see where your steel in your core and cavity interlock where I have these vent slots located. And typical shutoffs that you would require is 5 degrees. So I have, wherever steel is touching steel, it's on a 5-degree angle. That way, when the two halves of your tool engage and disengage, you have less sliding surface in the vertical, where that will eventually cause tool wear. So the more angle that you put on, the less sliding friction you have between your shutoff surfaces. Oops, that's a note to myself. But I'll show you how to use the mold tools. Let me get this set up here. Okay, here's a simple electronic enclosure. I'll go to my mold tools. I will perform a draft analysis to get everything started here. And I will select my parting plane surface along the part. I'll knock down the draft I'm analyzing down to 1 degree. And then, if you can see, there's an arrow here. This is your direction of draw. Well, the direction of draw is actually the opposite direction, so I'll just click the arrow in the manager, and the arrow shifts to the proper direction of draw. You can see the color settings here. I do have adequate draft running along on my cavity, and the red surfaces are all part of my core side of the tool. So it does look like everything is lining up correctly. Okay, what I want to do first here Okay, what I have to do is, you've heard of shrink in your injection molded parts. What we have to do is we have to incorporate the shrink into your tool. So if your part will, if the materials you select will shrink 0.003 of an inch per inch, for example, you have to increase the overall size of your mold cavity by that factor. So what I will do is I will go down to scale, and type in my shrinkage factor. So what this is going to do is it will enlarge the part by that 0.003 of an inch per inch uniformly throughout the part. Okay, so now that takes care of the shrinkage. Now I'll go to the parting line. Go back to my parting plane again. Make sure that use for core cavity split is checked. Run my draft analysis. Here again, the arrow is pointing in the opposite direction that I want, so I will just click the arrow here in the manager. That brings that up correct. Click on draft analysis, and here again, the proper core cavity surfaces are shown in the red and the green. Any questions on this? Okay, good. We'll check the green check. You'll see where the parting line is highlighted in blue on the part. Shut-off surfaces. Okay, between the core and cavity, I do have all these slots, cord holes. Those will have to be shut off between the core and the cavity. So I'll hit shut off surfaces, and you'll see here that wherever there is any interfacing between the core and the cavity in these slotted features or the hole features in the boss, each shut off is highlighted. What I want to do here is click on my green check. Calculating. Okay, now you can see where I have a shutoff here between my core and the cavity. These slots and these holes look correct, but if you look at this elongated feature here, you have this puckering of the shutoff surface running around this part feature. So what I'll do here is I'll go back, and you can see here that each shutoff is labeled. I will change that to tangent. You have 3 different types of patches for your shutoffs. No fill, all contact fill, and then a tangent fill. So I did change it to a tangent fill on this particular shutoff. And now that puckering is no longer there, and this is something that can be readily tooled up. Any questions on shutoffs?
Why did the shut-off surfaces on the bottom?
How did I?
You've got shut-off surfaces on your mounting bar.
Right.
Because that's 9 below.
Yes, yes. The software notices where the interface between the core and the cavity steel is. It will put a shutoff there to separate the two. Okay, parting surfaces. Now, I will go here, and now we're going to start to create the actual body of the tool itself, your core cavity halves of the mold base. Now this is where the core cavity split will occur at this yellow preview. But what I want to do is create a parting surface that is going to be the same size as my mold base or mold inserts. So I'm going to change that to 5 inches. And now I have a surface representing the core cavity split. Now what I will do next is I'm going to add the tool steel body by clicking on Tooling Split. Now what you do here is you select this surface and then sketch what you are going to be needing for your mold-based steel. So this is a rectangular sketch. I'll create this at 14 inches, this at 12. Click OK. And here. Okay. Now, I already filled out these fields practicing earlier. They're still here. But I have tool steel 4 inches on each side of the core cavity split plane. You can change this to 3. I'll just do that for now. And now you have your mold base or mold inserts, depending on what direction you're going on the tool. So from here, I'll expand my surface bodies in the feature manager tree. You can see cavity, core, parting surface. So what I want to do here is I'm going to hide those. I'll also hide the parting line. Just for visual purposes here, I'll just clean this up a little more. Okay, I'm going to split the two. Halves of the tool. And then last, I'll flip this over. Rotate the core side. You could also type in 90, but I'll do it this way. Okay, so now you have your core cavity split, your core, the cavity of the tool is created. So you do have your two halves. I did get a good core cavity split, so my part design does appear to be correct. Any questions on that? Okay, good. Oh, yes? Shrink for my material? Yes, it was the beginning step where I took the plastic part and enlarged it by a factor of 0.03 of an inch per inch overall. So that was taken care of. It's easy to just go down your mold tools list and just go down in the order that the tools are located on your toolbar there. Right, it will show an error typically at the shut-off stage where it's not separating the core and the cavity where the core and cavity are actually touching. It will show you an error indication at that point. So you have to backtrack and see what feature in your part did cause the problem with the shut-off. Okay, here's a slide just showing you adding the shrinkage. Okay, just get through here. Oh, one thing I want to show you, if you are going to, rather than make your mold halves, the core cavity halves, if you're going to be using an off-the-shelf mold base assembly, and I'll show you that in a moment, you will need to use the surfaces that you created here using the mold tools. The surfaces will end up being cutting. You will cut with surface into your mold base halves. So you will use these as a cutting tool if you are going to be using an off-the-shelf mold base. And I'll show you that here momentarily. Here's a PCS mold base that it's one of my favorite mold base configurations. I downloaded this from 3D Content Central, and you can see here that it gives you all the individual pieces that you would require for your mold base. So what you will do is in your A and B halves of the tool, you will take those surfaces and use those, locate them in your mold base, and then go insert cut with surface. And then you'll hog out your core and your cavity using those surfaces as your tools. Okay, now mold tools versus standard mold design practices. The mold tools, when it creates shutoffs, like in this feature here, it will take the part geometry, which is, I have 3 degrees draft on this particular snap fit. What I want to do is I want to create a shutoff interface at this point between the core and the cavity at a 5-degree angle. I mentioned shutoffs should be 5 degrees. That'll give you less friction. If it's at 3 degrees, you'll have more surface friction as your tool opens and closes. So 5 degrees gives you less wear over the life of the tool. Mold tools in SolidWorks will look at the part geometry, which was at 3 degrees, and create a shutoff like this. What I want is a shutoff feature like this at 5 degrees. What I ended up having to do is, during the shutoff phase of my mold, inserting my shutoffs for the mold in the mold tools toolbar, I did not. I used a no-fill shutoff condition here where it did not create my surfaces. What I ended up doing was I modeled in my own shutoff surfaces. I did surface lofts to create the 5-degree geometry that I have here versus the 3-degree geometry that's over here. And then I ended up knitting these surfaces that I had created with the rest of the core cavity split. Any questions on that? That might. On this side here, yeah, I think I used 3 degrees here originally, but I needed the 5 degrees, so I had to go in and manually construct these surfaces, which are at a 5-degree angle. Excuse me? I'm sorry, could you? Okay, oh, okay. Okay, when I modeled the part, I used a 3-degree draft on this feature here. I did want, because the rest of the tool is either at a 1 degree or a 3-degree angle, depending on what part of the geometry I had here. I do need the 5 degrees, so I had to go in and construct that myself. So the part itself was designed at a 5-degree shutoff, but SolidWorks mold tools saw it differently, and so I had to go in and reconstruct it myself. Okay, and then a standard shutoff for those snap hooks. You can see here where at the 5-degree angle, there would be less sliding friction when the two halves of the tool engage when the tool is closed. So I'm just showing a 5-degree shutoff angle does minimize the amount of wear over the life of the tool. So when you do have steel to steel touching like this in the vertical direction, it's always better to give more generous draft angle on those features. Okay, and here's some variations on the injection molding process. I just wanted to go over some of the variations so that you can see that the injection molding process is rather versatile, and you could add different features in the molding process to get different types of parts. Now this is a gas assist injection molded part. It's a refrigerator handle that I did for a durable goods manufacturer in Iowa, and it's a refrigerator handle. It's molded out of a plating grade ABS, and then there's a brushed nickel finish that was used to plate the part. The gas assist, what you do is rather than filling your mold cavity 100% with resin, you stop at about the 80% point of fill, and then you inject nitrogen gas, which will flow through the center of the part, which is still the most molten portion of your melt that has gone into the mold cavity. Your outer surfaces are in contact with your mold, so the plastic skin is already being formed and being set up. The material in the middle of the part cavity is still soft enough where when you inject nitrogen gas, it will inflate a channel running through the entire length of the part. You would have on one end of your part a gate and then a gas pin. Once the material goes through the gate roughly to the 80% fill point, nitrogen gas will be injected into that gas, through that gas pin, and form the hollow cross-section of this handle. Another use for gas channels here is a tote box where I have created gas channels running through these features running along the outside of the part. Those ribs help to stiffen up this tote bin. You can see where gas pins are located on the inside of the part, plus the gas channels here in red. And depending on where your gas channels are, your gas pins would have to be located for your particular design. That would be best left to the molder that you would use that is familiar with the gas assist process. Let them get involved in helping you mold the part. I would recommend, if you do look at gas assist for a process, you find somebody who does a lot of gas assist molding, and then take advantage of their experience and expertise and let them help you design the part. So get in touch with a gas assist injection molder early on in your product development. Gas pin location and quantity, again, here we are, the design tips, seek injection molders with experience with the process. Another application, creating structural channels. This was a treadmill that I was a part of a design team on, and my responsibility were all the major plastic parts. On the console here, this is the first all-plastic console that we had at Life Fitness. Typically, they were just a non-structural front panel with a fabricated sheet metal box on the back. That's where you got your mechanical strength, from the sheet metal box. This has both molded front and rear. The front half of the console has right angle and diagonal gas channels running through the part. So I actually molded an internal tubular structure on the front half of the part. And that has been a practice with Life Fitness since this treadmill. This was 2 generations ago, but they still employ the same method to stiffen up the front half of the console. Here's using living hinges. Excuse me. I did this disposable medical forceps about 15 years ago, where rather than having 2 separate halves and then having to assemble them as a secondary operation, I molded living hinges at these points to get the clamping action. So there was no secondary assembly required for this forcep. Here's a mechanical assembly that it is a safety cutoff switch for a treadmill. But I did not use any mechanical fasteners. All the fastening features to put this thing together were either molded in, or I'm using pressure-sensitive adhesives or cyanoacrylate in the secondary assembly. But there are no screws, brackets, Tinnerman clips, that type of add-in fastening components. Here's some details of the snap hooks. These were all cut into the tool so that I would get these little spring clips to hold in different components. One good practice, if you're going to have this type of detail in your mold, to have the tool components, the tool steel that is creating these particular features, have them put into your tool as inserts. That way, if they do snap and break, it would be a minimum amount of time that the tool would be down. You just go in, replace the inserts, rather than trying to cut out a whole portion of your tool and re-burn it in. So put in the service feature right at the beginning of the mold design, and you'll spend less time with your tool in the tool room. Here's something called plastic metal hybrid technology. It's well, like insert molding on steroids. This is a technology that has been used in the automotive industry in Europe a lot more than it has been used here in the States. But you have large sheet metal panels like a door, the exterior panel on a door, but a lot of your interior features, stiffening features, the window lift mounting areas, speaker locations, these are all injection molded after this large steel weldment was placed into the tool. So what we ended up doing here is the exterior body panel, the door, rather than having welded brackets and a whole substructure on the inside of the door, this was all injection molded. I think the current series of Audis have front ends that are molded like this, where headlight, radiator, your various turn signal indicator lamps are installed using this hybrid technology where they are mounted to plastic that has been molded as a secondary. Here's just one more example of that. One new molding process that I have gotten quite interested in, and I've only been able to do 2 jobs with it so far in the last 3-4 years. It's called microcellular foam molding or mucel molding. It's similar to structural foam, if you know what that is, where the interior material of your solid plastic part is cellular in nature rather than a solid homogeneous cross-section. And there are several different advantages of going to the mucel molding. The volume has to be up because the initial outlay on the equipment can be rather high for your molders. But there are a number of molders here in the U.S. that already have invested in the equipment. Hoffer Plastics in Elgin, Illinois is an excellent quality molder. They have a lot of vision. They have been working with this process for about 5 years and are probably the U.S.'s foremost expert injection molder in the mucel process. The cellular structure here is between 10 and 40 microns in cell size. So you can see that rather than having a homogeneous material, a cross-section, it is quite porous. But this does translate into reduced cycle times, less material usage, and a much stiffer structural part. Because it is a low-pressure process, sink and cosmetic issues can be minimized. So if you're having problems with standard injection molding and your aesthetics are problematic, this might be an alternative for you to use. I have gone down to 60 thousandths. Thinner than that point, I was told that you do not get an adequate microcellular structure. There's just not enough cross-section there. And now injection molding simulation, that's probably about 40% of my business these days. I do various types of mold design validation, process validation, but I also use it heavily as a design aid for the parts right up front. Again, that would be like the new add-in SolidWorks Plastics. I currently still use SimpleWorks, which has a couple more functions that SolidWorks Plastics doesn't have. SolidWorks Plastics gives you fill and pack data at the SolidWorks Plastics, premium and professional levels. If you want warp and cooling, where if you want to incorporate your cooling lines in your mold design and run a simulation with cooling, you do have to go to Simpo and get 2 add-in modules to add to SolidWorks Plastics. But I've been using Simpo for 4 years. I had used MoldFlow for almost 10 years before that. And Simpo is a much more intuitive, user-friendly package. They're in the partner pavilion, and if you are looking at the possibility of bringing in the higher end functions for injection molding, talk to them. If you're looking at SolidWorks Plastics for your basic fill and pack, talk to your resellers, because they have it available through there. But here, you work within a native SolidWorks environment. Here I have my cooling channels. These are just 3D sketches that I created of my cooling lines. And what SimpleWorks will do is it will take my sketches and create the cooling line geometry, the right diameter, my different cooling line designs are taken right off of the sketches. Prior, when I used to use MoldFlow, I would have to take a SolidWorks file, convert it to an IGES file or an STL, and then from there put it into MoldFlow. If I made a design change, I'd have to go back into SolidWorks, make my changes, create the IGES file, and then STL file, and then redo my simulation. With SolidWorks Plastics and Simpo, you don't have that intermediate step. You just use your SolidWorks files. Meshing the model, it is a very powerful meshing engine that is incorporated in SolidWorks Plastics and Simpo. You would end up meshing cooling lines as well as your part. Here is a close-up where, because the more complex your mesh, the finer your mesh, the longer your calculation time is going to be. So wherever possible, like in your nominal wall, I'm using a fairly coarse mesh where the nodes are quite far apart. But here in the vent slots, the boss in the corner, and the snap fit, I'm using a much finer mesh because I want more information, more refined information on the detailed features in the part. I don't necessarily need that for my nominal wall. So my file size would be smaller, would take less time to calculate. What's nice about the Simple Mesh, and they've added a new feature for 2013 that's not up here yet, but this hybrid mesh that they've created gives you a much more accurate laminar flow simulation as your part cavity is being filled with resin. It more accurately mimics what's going on with your material as it's being injected into the part cavity. You do have thousands of resins available in the material database, so you can really zero in on the material properties that you're going to be running your simulation with. Here, your molding press with all the unique mechanical properties are reflected in the selections that you have of your molding presses. There's hundreds of different injection molding presses listed in their database. For the cooling channels, you can regulate the flow of your coolant, the temperature of your coolant. You could go in and create settings that would reflect how you're going to be running your molding process, how you're going to be setting up your cooling conditions. You just go down the list and fill in the various parameters of your molding cycle and your material properties. You just go down the list. It's very straightforward. Nothing very complex about that. You can do sequential gating and filling where, say you have a long part and you have 3 separate gates. What happens is the first gate starts the fill process. As the wavefront goes past the second gate, material will start flowing from that, and then as you get to the third one, you will be able to replicate this process. A lot of large automotive parts uses multiple sequential gates, like a dash panel, an injection molded dash panel. It's so large you need multiple points to inject your material, but you also want to use the flow front and then sequentially open up gates that follow your flow front for an even fill. But you can simulate that in Simpo. Well, with the sequential gating, if you time it correctly, the material at each subsequent gate will just contribute right behind the flow front. We'll start filling right behind the flow front, so you do not get a separate flow front at each gate. You can do co-injection, gas assist, where the less expensive mold flow packages do not do that. I believe Moldex 3D does, but it's substantially more expensive than Simpo. You can do insert molding. When you think about all these contacts that are put into this injection molded part, those would impact the cooling portion of the cycle because you have all that metal in there. So it's good to, if you do a lot of insert molding, it's good to be able to incorporate all your inserts because it will affect the thermal properties of the molding cycle. You cannot simulate any sort of shifting of your inserts, if I followed your question. Yeah, well, they shouldn't. The inserts shouldn't be floating around in there. That's the tool maker's responsibility. But in an ideal scenario here, it will not tell you if your inserts are going to shift. I could do runner balancing for multi-cavity tools. It's very easy to set up as well. You learn a lot. You want all your cavities to fill at the same uniform rate, regardless of where it is in the tool. That way you will have uniform molding conditions in each of your different cavities. So runner balancing is an important factor. Here's a couple. Here are the people over at the Simpo booth at the partner pavilion. Just go over there. You don't need this information. You could get that from them over there. Final reference recommendations here. There is, if you're new to injection molding or just learning about it, this document is available from the Society of the Plastics Industry. You go online, they have an extensive bookstore that you can purchase a lot of these documents. The standards and practices of plastic molders. It gives you an idea of the most common resins that are commercially used, and it gives you a lot of the different physical properties, the shrinkage, minimum wall thicknesses that you can use for these different resins. And it gives you an idea of how a lot of your common materials properties behave. So this is not a bad document to have if you're still kind of on the learning curve earlier on. For tooling, if you are involved in selecting or specifying tools, this gives you a lot. This document, again from the SPI, gives you a lot of background information. Say automotive tooling would be made out of certain materials because of such high volumes and typically a lot of glass content in the materials. Whereas I've done some disposable medical packaging where the volumes are much smaller. I would not necessarily need that robust a tool steel for materials that I've used for the disposable meds. So it gives you an idea of the different levels of manufacturing volume that you would have to address when you're specifying tools. The last document I'd like to recommend is cosmetic specifications of injection molded parts. It's very difficult for your supplier and your incoming inspection to often agree on, what color is a black part. The cosmetic specifications document here discusses how to inspect with common practices that your injection molder can set up at outgoing inspection, which would correspond with your incoming inspection practices. So things like the cosmetic properties of a black part. One thing they would recommend is using a Macbeth light box, a light booth. It gives you standardized lighting conditions that you could set up in common between yourselves and your incoming inspection group and the outgoing inspection group from your molder. That way you can be inspecting things the same way. It shows you how far away, at what angle to the light you hold your sample parts so that everybody is inspecting the parts the same way. Life Fitness components were very cosmetic and we had a lot of issues before we went to a lot of the standard practices called out in this document. So this helped a lot. Okay, any questions? That's it for today. Yes? You would take your, if you have a standard mold base assembly and you have a core cavity inserts, you would insert the parts and then use move copy body feature function in SolidWorks to move your core cavity inserts to where you want them in your mold base. You can move them in separately. One more point. If you can fill out those questionnaires that were placed on the seats, we really read those things and they help us improve our presentations moving forward. So if you do have a chance, please fill those out. We do read them and SolidWorks reads them as well. So are there any other questions? Yes? I would have to think about that one. If you could give me a bit, maybe we can touch base on that as we finish up here. Are there any other questions? Okay, well, thank you for your time and attention. I appreciate it. And I hope you folks walk out of here with something new added to your knowledge base. Thanks again.